Hello everyone, welcome to this video in which I'm going to point out some potential misunderstandings and wrong interpretations in statistics that I found in engineering research papers. I'm going to consider three papers here, but in general, I have seen this kind of misunderstandings and wrong interpretations in most of the engineering research papers. Uh, the first paper that I'm going to consider is this paper here. Linear and nonlinear regression analysis on the prediction of compressive strength of sodium hydroxide pre-treated crumb rubber concrete. I must emphasize that I'm not going to I'm not trying to show some mistakes as such. I just want to point out these things uh, as a help for the young researchers when they are writing their research papers, not to make this kind of misleading or erroneous statements, which will reduce the validity of their papers. Right. Now, seeing this kind of mistakes in papers actually reduces the value of the paper and also the reputation of the journals also, because it shows that even the reviewers don't have the necessary knowledge to review the paper, but they have accepted it and passed the paper with these errors. So that is not a good thing, right? So therefore, I hope this particular video will help you to understand some common mistakes and errors and misunderstandings, so that you will be able to avoid that kind of errors in your research papers. That is the only purpose, not to uh, downgrade any paper or something like that. Right. So anyway, I have a copy of this paper here. Uh, so let me take that paper first of all to show you. Uh, so this is the paper that I'm mentioning here, considering here, linear and non-linear prediction. Yeah, this paper. Right. So let me start with it. This contains several such misunderstandings. So let me discuss each separately. First of all, I see there is a uh, wrong interpretation of a formula, right? So that is, I have mentioned here, definition of this R square is wrong actually. A major statistical issue is the formula given for R square here. This formula is mentioned in the paper. Right. Yeah, this is the formula mentioned in the paper. And it says after the model development, accuracy of the model depends on the error, which can be calculated with the help of statistics. Each error has different criteria to check the accuracy of the model. In this model, the first error evaluation method that was used was the R square coefficient of determination. Yeah, R square is called coefficient of determination. That is correct, but this formula is not the correct formula for R square. Actually, what you have here is only actually this is the square root of r square. So r square uh, is not this equation. This is the correlation coefficient. What you have here is the correlation coefficient between observed y values and the predicted y values. Right? R square is actually the square of that. So R square has to be square of this, not this one. So that is one error that has missed from both the author and the reviewer. And so this expression is the sample correlation coefficient between the observed values AI and the fitted values Fi. It's not R square. The coefficient of determination is the square of this correlation, provided that the model includes the intersect. Right. And then in the same paper, some terminology again regarding this multiple linear regression, nonlinear regression, and so on. The authors have fitted two models, right? They call them MLR and NMLR. I think non-linear or something. So they refer to this second model as a nonlinear regression model, and this one as a linear regression model, right? But actually, the term nonlinear regression and model is not really correct in terms of the terminology used in regression analysis. I have explained this clearly in my video regarding regression, right? In regression analysis, usually we use the word linear regression not to mean a straight line. When we say linear regression, it means the regression function that we consider is linear in terms of the parameters, not in terms of the variables. Right. But I think that this author has used the name nonlinear regression for this second model here because some quadratic terms of the variables are included here. There's a NaCO square, CR square, TP, NATP square, and so on. That may be the reason why he is using this the term nonlinear regression for this model. Actually, in the regression terminology, this is not a nonlinear regression model. This is a linear regression model. But in particular, when you have these power terms of the variables, we call it polynomial models, polynomial regression model. So therefore, the more correct word here is probably linear but polynomial regression model. The model is linear because the coefficients have power 1 actually in the model, right? The model is linear in terms of parameters. Therefore, it is a linear model. But because variables have power, second power, third power, and so on, we can call it a polynomial model, but not a non-linear model. I have explained, I have given some examples of intrinsically nonlinear models in my video on the regression analysis. So that is another misunderstanding, right? Just because these power terms of the variables appear in the model, we don't call it a nonlinear model. Although the model is nonlinear in the explanatory variable, it is still a linear in the regression coefficients. Therefore, from a statistical modeling point of view, it is more accurate to describe this second model as a multiple polynomial regression model rather than genuinely a nonlinear regression model. Right. So that is another explanation that is probably necessary here. And then in the same paper, I see probably some effects of probably the multicollinearity, which has not been addressed in the paper. So let me go back to the paper again. Right. So if I look at the fitted model here, two models, Uh, yeah. So this is the second model fitted. Let me look at the first model. Okay. So this is the MLR model. It contains all main effects only, but it contains some variables which are possibly highly correlated. It contains cement content. It contains water content, as well as it contains water to cement ratio also. So it's very possible, highly possible that these variables are somewhat correlated, maybe highly correlated. Right? W divided by C is the amount of water uh, divided by cement content. Right? And why do I think that there may be possibly multicollinearity? Because the physical interpretation that from the things that we know doesn't go with this. For example, if we look at the practical situations, the model includes cement, water, and the water cement ratio W divided by C, that is the label, uh, as explanatory variables. Since W per cement is calculated from water and cement, these variables are naturally related. Right? These three variables are naturally related. Including all three in the same regression model can create multicollinearity. Right? As I have explained in my video on regression, multicollinearity can create some problems. One main problem is the instability of the fitted model. Fitted model is unstable. That means uh, just by changing one or two observations, regression parameters, fitted regression parameters can be quite change quite a bit. And also sometimes even the sign of the coefficients can change, which is very, very showing the instability of the model. Right. So multicollinearity can make estimated regression coefficients unstable and difficult to interpret also. For example, in this fitted model, the coefficient of W over C in the MLR equation is positive. Although concrete strength is usually expected to decrease as the water cement ratio increases, when other conditions are controlled. Right? So suppose the other conditions are keeping fixed, where we increase the water to cement ratio, then usually we know in practice, when the water to cement ratio increases, the strength decreases. But here in the fitted model, we see that the coefficient is positive here for W over C. So that is practically not a meaningful thing. Though we don't expect that kind of thing practical. So this might have occurred due to multiple linearity. It's possible, right? And in the second model, when they have included these square terms, in that one, of course, this quantity W over C has now the coefficient has been changed to negative, right? So that is also a problem. In one model is positive, the other model it's negative just by adding some more variables. That again may be due to multicollinearity, because otherwise it has to keep the correct sign most of the cases, right? If it is changing the sign from when you are adding some variables, that is also showing the instability of the model, right? And also, so how is it possible to reduce this? Right. First of all, we have to check whether there is multicollinearity using variance inflation factors. I have discussed this thing in my regression video, right? Usually, if the uh, variation in inflation factor is greater than 5, it's considered a significant serious, but at least worth considering, worth investigating. And if it is greater than 10, it's very serious, right? Multicollinearity problem and must be tackled with, must be solved. That problem must be solved, right? So here, what sort of things could have been done? For example, usually when you have this polynomial type, here also they are, in the previous one, multicollinearity can occur. Here also multicollinearity can occur because, for example, you have, sodium concentrate and sodium concentrate square. Those are also correlated to a certain extent, x and x square, right? So in that way also multicollinearity can be created. So therefore, when you have this kind of polynomial regression models, it's better to consider standardized variables rather than original variables. By doing so, you can reduce the possibility of occurring multicollinearity. I have shown this in one example in my regression video. And also, I see that in this paper evaluates models using only R square, MAN, root mean squared error. It has never looked at any residual analysis, right? So when you don't do residual analysis, you don't know whether the model assumptions are satisfied or not. Therefore, we don't have any idea whether those p values on which you have already made some decisions are valid or not. So therefore, that is an important part in whenever you are carrying out a regression analysis. Either show some of those uh, residual analysis outputs and then interpret them and show that the model satisfies the data satisfies the model assumptions and so on. That is important, right? In most of the regression analysis in engineering papers, I have not seen any residual analysis. And also, it talks about some high R square value and high MAE and root mean square error values. But those have been calculated only using the uh, one part of the full data set. The data set has not been divided into two parts, one part to fit the model and the other one to validate. There has been no such partition in the data set, right? So these R square value high, so-called high R square values actually have come from the original sample from which the model itself was fitted, right? But what is most important is that we have to have a high R square from the validated data set also. If you put the same model to validated data, still we should have high R square. Then only we can say our model has a predictive power, right? That has not been done in most of these papers. Of course, I understand that in engineering, usually you don't have very large data sets to consider two parts like that. But whenever possible, it's better to have some repetitions or replications under each condition so that at least some of the values will be in the model fitting part and then the other one will be in the uh, prediction part. Sorry, I mean validation part, right? So those are some weaknesses in that particular paper. Now let me look at another paper called Mechanical and Thermal Properties of Interlocking Bricks Utilizing Wasted Polythene Terrapolythene uh, or something like it's very difficult to pronounce also. So what are the problems in this paper? The main statistical performance measured emphasize the paper is in this paper is a coefficient of correlation between observed and predicted values. So that is actually not a good way to measure the uh, statistical performance of a model, right? What they have done is they have calculated the correlation coefficient between the observed y values and the predicted y values. But you already know, as I explained in my correlation analysis video, this usual Pearson correlation coefficient measures the strength of the linear relationship only, right? And it's not used as a general measure of uh, the statistical performance of a fitted model, right? So, but the paper reports very high correlation, approximately 99.99. That's as a percentage, or 0.999 as a correlation. But this is probably not an indication of the goodness of the model. It may have probably happened because the model has overfitted the small data set, right? They have a small data set and the fitted model is kind of overfitting with too many parameters in the model, right? So if you are fitting a model with, for a small data set, a model with large number of parameters, it tends to overfit, right? And that's not considered as a good model, especially considering the parsimony principle and so on. For example, just to take an extreme case, suppose, for example, your predicted values are, all the predicted values are equal to the observed values plus some constant. That means y hat is equal to y plus k, that kind of model, with a very small error term, for example. So if this is the case, for example, correlation coefficient will be very, very high, right? It will be almost 1. But it's not a good model, usually, I mean, if you have that kind of situation, right? So we should look at better measures of the performance of the model, right? Especially, again, whenever possible, you should check the R square value and other quantities for a validation data set rather than for the data set that you considered for the fitting of the model. So in this case, the very high R square, correlation coefficient is not necessarily an indication of a good fit, but probably it's an overfit. And in this paper also, they have never carried out any residual diagnostics to check whether the model assumptions are reasonable or not. So that is a big weakness. Right. And now I will look at my third paper. This has a title Regression Models for Prediction of Compressive and Tensile Concrete Strength. Uh, in this paper, there is again a commonly made misunderstanding. That is interpreting the R square and adjusted R square values as prediction accuracy. This paper interprets adjusted R square as prediction accuracy. For example, an adjusted R square value of 0.884 is interpreted as 88.4 accuracy. And actually, this interpretation is not statistically correct. What R square is actually is the proportion of variation, total variation in Y, that can be explained using your model, right? When you use X's to predict Y, using that model, you will be able to explain a part of the total variation in Y using the model. So R square gives you that part out of the total variation in Y as a percentage or as a decimal number, right? But it is not actually giving you any measure of the accuracy. It doesn't say that 88.4 of your forecasts are correct or something. It's not, it cannot be interpreted in that way. So therefore, that interpretation of saying 88.4 accuracy is not really correct. R square can be interpreted as the proportion or the percentage of the in-sample squared prediction error reduced by the fitted model relative to the predicting every observation by the sample mean. So that means if you don't have any information about X's, you will use Y bar to predict as the predicted value of all the Y values, right? So by that way, you will be making some errors. So if you consider the sum of squares of those errors, that is the sum of squares of errors or variation in Y in your prediction if you don't use X or you don't use the model to predict. And now if you fit the model and use that to predict Y, in that case, there will be some errors, and sum of squares of those errors are the ones that is called residual sum of squares, right? So there's a difference between the uh, variation in Y, that is the sum of squares of errors that would be obtained uh, in predicting without using X. And if you consider the sum of squares of errors that will be making, if you're using the model to predict Y, there will be a difference between those two. And that difference as a ratio to the total variation is called the R square. So that's why we interpret it as the proportion of variation in Y explained by the model, right? But it doesn't say that 88.4% of the predictions are correct or something. It doesn't say that. So therefore that uh, should be interpreted correctly, right? And also in this paper, they have used some other quite meaningless method to for the model validation, right? The paper states that statistical t-test shows that there is no significant difference between the observed and predicted strengths. So the strength is the Y variable that they have used here. So what they have done is they have obtained the predicted Y values and the observed Y values and then compared those two using t-tests. But the t-test that they have used is the t-test that is used to test whether the two means are the same or not. That is to test whether the difference between the means is equal to 0, right? So test value is 0 here, right? What they have done used is actually two independent sample t-tests also. That is even more wrong, right? Because in this case, you are considering Y and Y hat related because all those Y and Y hat values will be related, right? And also comparing those two using t-test also, in that what they are trying to do is to compare the mean of Y values with mean of predicted values. Using the t-test, that's what you can do. You can compare the mean of Y values, but that is again meaningless in this case. And if you want to do it anyway, for some reason, then you'll have to use the paired t-test, for example. But this independent sample t-test will not be meaningful at all. It's completely wrong. And we don't want to, there's no point of comparing the mean of y values with mean of predicted y values. What we want is individual y hat values to be as close as possible to individual y values, right? You can have means to be equal even though they are completely different, right? For example, positive values with negative predicted values, still the means can be equal, right? So this is completely a meaningless thing to do, right? So like that, there are so many errors and meaningless things and meaningless interpretations in research papers that I looked at. So this, I think, I hope at least will help to certain extent, to at least to a little extent, for you to not to make that kind of mistakes in your research papers. So I will end my discussion here because I don't want to take too much time. There is another one that I forgot to mention. And actually, for example, in engineering experiments, usually you consider, for example, concrete mix proportions. But a concrete, when you say mixture, in the mixture, the proportion of those quantities involved add up to something, and that is usually a constant. So therefore, there are some constraints on the amounts of different components in the mixtures. Right? You cannot consider them as independent numbers. For example, if you are considering, for example, percentage of cement, percentage of water, and percentage of some other chemical, these percentages should add up to 100. Right? So therefore, whatever even though you change the values, their percentages always are adding up to 100. Right? But in most of the regressions, they have used this kind of percentages. They have ignored this fact that they are constrained by some formula, right? So therefore, actually, these three things or four things that you are considering cannot be considered as completely independent quantities. And if you include all those, for example, three quantities, percentages in the model, it's very possible that again multicollinearity problems can occur because some of these three things add up to 100. They are mathematically linearly related. So then when you are using the least square regression method, for example, in some matrix inverses, those inverses either you cannot calculate those inverses, so they will be very, very unstable. Right. So you'll have to consider that kind of situations also when you are using that kind of variables in the regression. Right. So that is the end of this video.